Hello everyone, welcome to the next lecture in the course Remote Sensing Principles and Applications. We started discussing about the various remote sensing platforms from which we can observe the earth surface. We discussed about ground based platforms, aerial platforms, and we started about discussing the space bound platforms, that are satellites, and today in this lecture we are going to continue with that particular topic. In the last lecture I told you about satellites, how to calculate the or what is the relationship between the orbital height, the velocity with which the satellite revolves around the earth surface, and the time period taken for the satellite to complete one orbit around the earth surface. We assumed a circular orbit while calculating all these things, and for all practical applications we can consider the orbits of remote sensing satellites as circular. They are not exactly circular, but we can treat them as so, with many minor differences will be coming between what we calculate and what the actual values are. And also in the last lecture we got introduced to the concept of inclination of the orbital plane, that which the plane in which the satellite revolves, we call it as orbital plane, the inclination of that particular plane with respect to Earth's equator, and also what is known as a orbital longitude, or more precisely the right ascension of the ascending node. So, with this background we will just look deep into the different kinds of orbits available for satellites. So, based on the altitude of the satellite above which it is revolving around the earth surface, we can classify the satellite orbits into three. One is low earth orbit, where the height of the satellite will be something around 200 to 2000 kilometers above the earth surface. Then comes medium earth orbit, in between them 2000 to about like 35,000 kilometers, and high earth orbit above a threshold of like 35,700 kilometers, or roughly 35,800 kilometers. So, this is based on the orbital height above the earth surface. So, with this, most of the remote sensing platforms or remote sensing satellites will orbit in the low earth orbit, roughly in the range of say less than 700 or 800 kilometers mostly. There are certain platforms which are available at high earth orbit, like around 36,000 kilometers, it is there, that are like geostationary orbits, which we will see later. So, this is based on the orbital height. Similarly, based on like the direction also, we can classify whether the satellite is moving in a prograde direction or retrograde direction. This I told you in the last lecture itself, but just like I am reiterating it, that is, earth is revolving in one particular direction or rotating in one particular direction. If the satellite also rotates around the earth in the same direction, we call it as prograde. Okay, the orbit is prograde. If the satellite revolves in opposite direction to the earth's surface, we call it retrograde. Okay, so these two are like technical terms which we should remember. And when I discussed about like orbital inclination, based on the orbital inclination there will be like a change in coverage of the earth surface. That is, if a satellite is having an inclination of I degrees, then, and if the satellite is in prograde orbit, then the satellite will cover latitudes between I degree north to I degree south. That is, let us say a satellite is in orbit which is inclined at say 55 degrees with respect to equator in prograde. Okay. Then that particular satellite will cover 55 degrees north to 55 degrees south latitude. It will not cover the entire globe. The satellite will be able to cover places occurring within this particular band, 55 degree north to 55 degree south. On the other hand, if the satellite is in retrograde orbit, like with the given inclination of I, then the latitudinal coverage will be 180 minus I. Let us say some satellites or most of the remote sensing satellites will be in the range of say 98 degrees inclination, and it will be retrograde orbit. Okay. So, with 98 degrees inclination means 180 minus 98 will give us 82 degrees. So, those satellites will cover Earth's surface between 82 degrees north to 82 degrees south. So, that is how the coverage will be. Okay. So, this is with respect to direction and as well as the inclination, the coverage of satellites will vary. First we will start discussing about the high earth orbits. One of the major or primarily used high earth orbit is geosynchronous orbit. In addition to geosynchronous orbit, we also have what are known as Lagrange points in which satellite can be positioned to observe Earth surface. There is actually like a satellite which is looking at Earth surface from one of the Lagrange points. We will see it in the forthcoming slides. What exactly is a geosynchronous orbit? A geosynchronous orbit is an orbit in which if a satellite is placed, it will have a orbital period equal to one sidereal day. That is, Earth is here, the satellite, let us assume the satellite is here, I is equal to 0, let us assume, inclination is 0, it is on the placed on the equator. If the satellite moves with the same speed as that of Earth, say Earth rotates with some velocity, if the satellite revolves around the Earth with the same velocity, then by the time Earth completes one rotation around itself, the satellite will complete one full revolution around the Earth and come at the same point. Such satellites are called to be placed in geosynchronous orbits. So, in geosynchronous orbit, the time period of one orbit or the orbital period for one revolution of satellite is equal to the time taken for Earth to complete one full rotation around itself. In this particular slide, I have mentioned about sidereal day. What exactly is sidereal day? Normally, when we learnt about like in school, we learned that Earth takes 24 hours to complete one rotation around the Sun. But the actual time taken for the Earth to complete one full rotation is actually less than that. Why is it happening? Let us see with kind of like a very small illustration. So, let us say this is Earth, let us assume this is the reference point I am taking on the Earth surface. Now, this reference point is seeing the Sun center. Okay. Now, the Earth is rotating around itself. At the same time, the Earth is revolving around the Sun in an elliptical orbit. So, the Earth is simultaneously rotating around itself and also revolving around the Sun. So, what will happen is, let us say this point is actually Earth is rotating like this. So, when we will say one full rotation has been complete, we will say when the same point completes this circle and comes to this same starting point, right. So, this particular arrow is our reference point. So, by the time Earth will complete one full rotation around it, that is the starting point has reached its origin, but due to Earth's motion or Earth's revolution around the Sun, the Earth would have moved away from the Sun. So, by the time Earth completes one full rotation around itself, it will not be able to see the Sun because the Earth has moved little bit further in its orbit around the Sun. So, what it should do? The Earth should make more than one full rotation around itself in order to see the Sun again. So, this time period taken for Earth to complete one full rotation around the Sun is 24 hours. So, from this we can infer that the time taken for Earth to complete one full rotation around itself is actually less than the time taken to complete one full rotation with respect to Sun. So, this basically happens because Earth is not only spinning around its axis, it is also revolving around the Sun. By the time Earth complete one full rotation around itself, due to its forward motion in its orbit, the reference point from where Earth started rotating, where we assumed as the reference point, it will not be positioned seeing the Sun, it will be positioned further away. So, the Earth has to make more than one rotation to complete one full rotation about the Sun. Okay. So, in 24 hours, or I will convert it into seconds, this will be 86,400 seconds, Earth will complete one full rotation around itself plus 1 over 365.24 rotation. So, one full rotation around itself is this reference point came here like exact full circle, but in order to see the Sun, it is making a slightly more than one rotation it is doing in order to see the Sun, and that rotation in a day will be 1 by 365.24 because Earth takes 365.24 days to complete one full revolution around the sun, and this is 1 out of the 365.24 days. So, in order to make this much rotations, Earth takes 86,400 seconds. This is what we know, the time taken by Earth to complete one rotation around sun. So, the actual time taken for Earth to rotate around itself is what we call the sidereal day, and the time taken will be 86,164 seconds. So, the sidereal day for the Earth to rotate around itself is actually less than a mean solar day, which is 24 hours. Okay. So, that is the time taken or the time taken by Earth to complete one rotation around sun. So, the orbital period or the rotation time taken for Earth is actually one sidereal day, 86,164 seconds only with respect to itself. Say for example, you can think this as of like kind of rotating in a merry-go-round or something. Let us say a person is standing in center of merry-go-round. Let us say you are spinning around yourself, you are also coming in rotation. So, by the time you complete one rotation around yourself, you would have moved in the merry-go-round, you will not be able to see the person. Either you have to tilt your head or go slightly further in order to see the person again. Similar effect, Earth is rotating around itself and also it is moving further, which is slightly increasing the time taken to complete one rotation around the sun. So, for geosynchronous satellites, the period of revolution to complete one orbit is one sidereal day, 86,164 seconds. By the time, let us say Earth is here, this is the reference point in Earth, here is the satellite. So, the satellite and Earth will move synchronously, we call it as geosynchronous. Geo means Earth or related to Earth, synchronous means they are somehow linked with each other, both of them move in tandem. So, this is Earth's reference point, this is here. So, they will move like this, and by the time this reference point come here again, satellite also will be here. So, the velocity period is exactly one sidereal day, 86,164 seconds. In this geosynchronous satellite, we know like the satellite rotation revolution speed is synchronized with Earth's rotation speed. Within this geosynchronous orbit, there is a special orbit in which if the I is equal to 0, like if the inclination is 0, the satellite is placed exactly over the equator and the direction of motion is prograde. Prograde means it is moving in the same direction as the Earth. Then what will happen? The satellite will appear as if it is constantly overhead over a particular point on the Earth's surface. That is, let us say this is like one particular city in India, let us say some satellite is positioned over Mumbai. So, what will happen? Like Mumbai is more than above 0 degrees north, but let us assume it is placed over certain location which is at 0 degree equator. Okay. So, as the Earth rotates, the speed at which the satellite rotates also will be synchronized. So, the same place in the Earth will be seen by the satellite continuously. So, such orbits in which if the satellites are placed, if they are able to observe the same spot on the Earth continuously throughout its lifespan, we call the orbits as geostationary orbit. So, a geostationary orbit or orbits which are like a special kind of geosynchronous orbit in which I is equal to 0. So, I is equal to 0 means the satellite will be stationed over one particular location on the Earth's surface. Now, let us think briefly. So, what will be the major purpose of launching a geostationary satellite? A geostationary satellite should look at the same location again and again. So, the first major purpose for which geostationary satellites were launched was communication. That is, in order to achieve like global communication through satellites, geostationary satellites were placed in different longitudes around the Earth. Okay, so, they will be able to constantly watch over a region and relay communication signals. That is, let us say this is Earth, this is the equator. Let us say there will be like lot of longitudes on the Earth's surface, we know that. let us say a satellite is positioned here. Okay. So, this particular satellite will be seeing one full region of this earth, like what I am shading now. Okay. This particular shaded portion will be like one example I am telling. So, this particular satellite placed in the orbit will be constantly seeing that particular region throughout its lifespan. It will not be in a position to see other parts of the globe. It is going to observe only that particular part of the globe. That means it will be useful for communication purposes, and also lot of weather monitoring satellites are put in geostationary orbits. So, for weather monitoring satellites, that is when we want to get data continuously, like there may be a large hurricane going in towards a particular country. These weather monitoring satellites may acquire images once every 15 minutes or so. So, for such high temporal resolution imaging, people place weather monitoring satellites in geostationary orbits. So, the major purpose of placing a satellite in geostationary orbit is for weather monitoring applications and also for communication purposes. And nowadays, like the data from weather monitoring satellites are very much useful in remote sensing, like India has INSAT 3D meteorological satellites, it had Kalpana 1, those are all majorly launched for meteorological applications, but they also have applications in earth resource, like for earth surface monitoring for remote sensing. US has geostationary operational environmental satellite GOES, there are satellites called Meteosat, there are plenty of satellites for remote sensing applications placed in geostationary orbits, constantly looking over a particular location on the earth's surface. That means it will cover only one region of the globe continuously, it will observe. Okay. Maybe we did not discuss the orbital height at which the satellite should be placed. That is, like in the initial point where we started discussing about satellites, we learnt that based on the orbital height of the satellite, its velocity will vary. So, here we need the velocity of satellite to be synchronized with of earth's surface. Okay, so, we can use the earlier equations which we learned in the last lecture, like using the time period. The time period is 86,164 seconds. If you substitute that equation, if you substitute this time period in the equation relating time and velocity as well as the orbital height, we can calculate these satellites has to be placed at a height of approximately 35,800 kilometers. That is, the orbital height h will be approximately 35,800 kilometers above the earth's surface. So, such orbits with this much altitude and the satellites having a time period of rotation of 1 sidereal day is geosynchronous satellites, and if I is equal to 0 for geosynchronous satellites, they are called geostationary. And the next question I posed is, will the rotation of geosynchronous satellite will be prograde or retrograde? It will be prograde. For geostationary it must be prograde, because if earth rotates like this, satellite also rotate in the same direction so that it can see the same point. If the orbit is in retrograde, then earth will be moving like this, satellite will be moving like this, it will not be seeing the same spot, it will be seeing different spots on the earth. Normally that will not be done. And also if an orbit is in retrograde along the equator, the I we will not call it as 0, we will call it as 180 degrees as a convention, because as a convention inclination angles I 0 to 90 degrees, we call them as, for prograde direction we assign them numbers 0 to 90. 90 to 180 degrees inclination we assign numbers to orbits which are in retrograde. Okay. So, for geostationary satellite I is equal to 0, direction motion is the same direction as that of earth's surface. This is one thing. And also one more question I would like you to think is, geosynchronous satellites with I greater than 0 is extremely difficult to find, almost not there to the best of my knowledge. Why is it so? The reason for this is, the major purpose of launching a satellite in geosynchronous orbit is to achieve this geostationarity, to look at the same spot on the earth again and again continuously. If you put any orbit other than 0, like if you put inclination other than 0, then this geostationary nature will go off. That is, let us say we have a satellite say this is Earth. Let us say this is like one geostationary orbit, this is the equator. Let us say I is equal to 10 degrees, okay, just for an explanation. Even if it is geosynchronous orbit, what will happen is the period of revolution will be okay, like it will be synchronized with Earth. But as the Earth rotates, the satellite, due to its orbital inclination, will be moving like in an inclined plane like this. Okay, Earth will be moving like this, satellite will be moving like this. So, essentially what will happen? It will not be stationed over one particular region, it will move from 10° north latitude to 10° south latitude, right. We have seen this, the orbit will be moving like that. So, it will not be covering one location, it will be covering different portions of Earth. So, that stationarity will be removed from it. So, normally for remote sensing applications, satellites with I greater than 0 will not be launched, they will be launched only in geostationary orbits. Okay. So, there are like conditions. So, geosynchronous means H is equal to 35,800, time period of rotation is 1 sidereal day. This is geosynchronous, general nature. For a geosynchronous orbit to be geostationary, I must be equal to 0, in which the satellite is rotating in a prograde direction. This is like a very simple overview of geosynchronous and geostationary orbit. So, as I told, the main purpose of launching a satellite in geosynchronous orbit is to produce or observe the same spot on the Earth continuously. An example is given in this particular slide. You can see a satellite is centered over like African continent. So, whatever be the time period, the satellite is observing the same spot again and again. Say this is morning 11:45 am local solar time. So, this will be daytime here, sun is here in this direction, okay, and this is afternoon. So, this is like afternoon, this is like evening. You can see like night is beginning to fall, and at night 8:45 this is night time here. So, essentially the same spot will be continuously observed over different time period. We can see like how clouds are moving in different time instances, and these kind of multi-temporal images even within a day will help us to understand highly temporal or highly varying factors such as cloud formation, hurricane movement and etc. Those are all the main applications for launching a satellite in geosynchronous or geostationary orbit. So, this is like a small video I would like to present where you will be able to see the beauty of the observations from geostationary orbit. So, this video is like produced by NASA in order to tell us how season varies basically. Okay. So, this will again observed over a satellite positioned over like African continent. Maybe I will just tell the context. This video is a combination of images acquired by a satellite over one full year at morning 6 am, I think 6 or 6:30 am roughly, that is in the same time period what I want to say. Same time period in the morning, so observed over one full year. So, sun is always positioned like this whenever the image is taken, like it is always on the right side from our point of view. The image start date is 10th September 2019, it moves all the way up to next year 11th September 2019. Just see how sun's light varies with different days. This is actually to depict seasons. You can clearly see like how the sun's radiation varies on the Earth's surface from North Pole to South Pole. This is actually the seasonal effect, how season changes. So, these sort of images, this is not to explain geostationary observation, but this is like way to explain seasons. This is like produced for school kids to understand seasons by NASA, but here I am showing this particular video just to show the beauty of geostationary observations. Same location, if it is observed continuously, we will be able to understand or comprehend many more things. Okay, that is the main reason. And also like I told you about equinox, right, vernal equinox, when I described about orbital longitude, right ascension of the ascending node, right. That can also be understood from this particular video. That is, when the video starts, the earth surface is, it was standing somewhere here, let us say. Okay, it was standing somewhere here. Basically this position indicates equinox, that is this is north, south, east, west, something of like that we can map. So this is one full circle of earth which the satellite is seeing. So basically on equinox sun will be overhead the equator. So one half of the globe will be exactly illuminated, giving rise to equal day and equal night time for places around the equator. So this time 10th September we call it as like autumnal equinox. Okay. That is sun is moving from north to south, it is crossing the equator during that time, that is autumnal equinox. So that will be indicating the winter season for the northern hemisphere, summer season for the southern hemisphere. Like observe this video carefully around this 11th March, when the time period crosses 11th March here, again it will cross an equinox, that is sun is move from north to south, then again it will start moving from south to north, again it will cross the equator. That particular day in which sun crosses the equator once more, we call it as vernal equinox. Vernal equinox is sun is moving from south to north. You can think it of as an ascending motion. Okay. So that day is vernal equinox. So this is just to explain those concepts, but this kind of observation is possible from geostationary satellites. We can even learn about different things which we haven't seen from any other perspectives. So just for that particular reason I showed this particular video. So the next kind of orbit what we are going to see is Lagrange points. So these are not exactly orbits I will say, but these are certain points. If two bodies are moving with respect to each other, due to the combined gravitational effects, there will be certain points around their orbit which will be fixed in space. That is, let us say this is sun, this is earth. So earth is moving around the sun in a fixed orbit, right. So sun will have a gravity, earth also is having gravity. Due to the combined gravity effects, there will be certain points, and if certain objects are placed in those particular points, those objects will appear in the point continuously. Say earth and sun is here, earth is here, both of them are moving, means those 5 points labeled here as L1, L2, L3, L4 and L5, those 5 points also will move with them. Such points are called Lagrange points. Okay, so there are like detailed physical explanation of why these points are there and all. We are not going to discuss in detail about those points, but the one thing what I want to mention is this is because of the combined gravitational effect of two bodies. Not only with respect to sun and earth, even with respect to earth and moon, you can fix 5 Lagrange points around it. So at those 5 points, if you place some objects, they will be kind of moving along with these two objects in tandem. Okay, so they will behave as if like a system. Those points are called Lagrange points. In this 3 Lagrange points L1, L2, L3, they are actually located along the line joining sun and the earth. One L1 between sun and the earth, L2 beyond earth, L3 beyond the sun. L4 and L5 are at points on the vertex of an equilateral triangle, that is this triangle, it is actually equilateral triangle. So one vertex is sun, one vertex is earth, one vertex is that L4 point. Sorry. Similarly, one vertex is sun, one vertex is earth, another vertex is L5 point. So totally 5 Lagrange points will be there for a two body system, sun and earth and moon and so on. So it will be like a two body system. So there will be 5 Lagrange points, you can fix it. So as the system moves, the 5 Lagrange points also will move. Among these 5 points, L1, L2, L3 are relatively unstable points. That is, if you place some object there, very easily they will move out of that particular point. So we have to maintain some or provide some force to it in order to keep it there. So these points are unstable, but L4 and L5 are highly stable points. If you place certain objects there, it will be remaining there. Okay. So, natural like people are telling like whenever there is kind of like a two body system like a planet and its satellites, normally some kind of asteroids will be coming in and located in the L4 and L5 points because of this combined gravitational effect, it is observed. So, this is like naturally occurring points, it is not like man designated orbit, these are like naturally occurring points because of the combined gravity. Okay. So, if we take a look at this L1, L2, L3 points, we can observe Earth from L1, L4 or L5. Basically L4 and L5 are like pretty large distances, we will not use. Normally we will use L1 for observing Earth, and then L2 point is beyond Earth. So, this is useful for astronomical applications. There are satellites placed at L2 observing the outer space. L3 we will not use because L3 is beyond the sun. So, whatever the data collected by this L3 satellite will be very difficult to reach the Earth since it is at very extremely farther distance. Okay. Sun is in between, so we will not get any signal. So, L3 will not be of much use. L4 and L5 are useful for solar observations, that is with respect to Earth they are very far, we may not get any meaningful data, but they are useful for solar observations and again outer space observations. So, these 5 points are called Lagrange points. So, as a summary, in this lecture we discussed about the classification of satellite orbits with respect to orbital heights. We discussed about geosynchronous orbit and as a special case geostationary orbit, and also we discussed about the Lagrange points. With this we end this lecture. Thank you very much.